Okay, we can start.
Okay. Hi, my name is Caroline Sabty from the German University in Cairo. I will be presenting our work about data augmentation techniques, Arabic data for name entity recognition. First of all, I think we all know here that we have a problem compared to the English resources for the Arabic resources and the Arabic data. And most of the natural language processing tasks require having large training data sets. And in Arabic, we have variations for the Arabic language, and we have less resources compared to the English, and especially for the code switched one. So what's code switching? Code switching is exchanging between different languages in the same context or in the same conversation. So we have recently, we can see more that in Arabic countries, we have multilingual speakers due to globalization and high education levels. People exchange between different dialects or between their own dialect and foreign languages. Like, for example, in North Africa and Lebanon, people could switch between Arabic and French. And Middle East, including Egypt, people could switch between Arabic and English. We have three main types of code switching. We have the intersentential code switching, which is exchanging between having a full sentence written in a language and another sentence written in another language. And we have the intrasentential code switching, which is exchanging between the languages in the same sentence. And we have the intra-word code switching, which is exchanging between the different languages in the same word. And we refer to these types also with code switching and code mixing. However, in this work, we refer to the types, the second type, the intrasentential, by code switching. One of the tasks that we decided to tackle the problem of data resources or less data, which is the name entity recognition. As you might all know, name entity recognition, or NER, is recognizing spans of text and that refers to real-world entities and assigning categories to these words, like, for example, person, location, or organization. Having the example, Sarah lives in Cairo, we can tag Sarah by person and Cairo location. This task is proven to be very significant, and it's a building block in several NLP tasks. So we have a limited data problem, and there are several approaches that were provided to tackle this problem, like the traditional one, collecting and annotating new data manually, using active learning, which is manually labeling part of unlabeled data and selecting this part by specifying what are the most informative, and by using data augmentation technique. This is the technique we applied here. The data augmentation is automatically creating new labeled data from existing ones. And this technique tackles the problem of having less data, and as the manually collecting and annotating the data is time consuming and more expensive, this technique was proven to be well and successful in image processing. However, it's less studies in NLP field and harder applied on text. Some of the related approaches or the general techniques that were applied before on NLP or on text, which is the lexical substitution, like using classical word embeddings, contextual word embeddings, and using back translation, or using generative models to generate new artificial data. We can see that we have some challenges for applying such technique on the Arabic language in general, and on applying on code switched language specifically. The problems are that we have to make sure that we generate realistic textual data, and you have to create natural switching points, like having what happens in real conversations. And in a problem like classification problem like the name entity recognition, we have to tag such generated data. We can see that one of the challenges that not all the existing or successful data augmentation techniques applied on text could be applied in such classification problems. Like, for example, the random swap will not add anything in such case. Our proposed techniques, we implemented 3 simple techniques. The first one is word embedding substitution. The second one, we modified a well-known technique, which is the AZ data augmentation technique, ADA. And we have the back translation technique. This is a general architecture of the augmentation process. We start by having our NER corpus. It's already labeled corpus that we have. And then it's a code switched as well. And we process the data. And then we have our augmentation module and then our tagging module. If the data or the tagged word, if the word augmented word is seen before in our corpus, we can get the same label. However, it's a new word. We have 2 taggers, one for English words and one for Arabic words. Starting by the first technique, we have the word embedding technique. We have 2 variations of this model. One of them is replacing only the entities with similar ones. We used 2 main variations of this model. We implemented one for classical using fast text and using another one for using contextual embeddings, BERT and Kermit, that we will talk in details about. And then if the word is an entity one, it's easy to have the same label of the one that is being replaced. This is the architecture of the classical word embedding substitution. As we said, in the classical one, we used fast text. So in fast text, we implemented 2 variations of this model, one for full replacement of the sentence. So if we have here the data set, and we can get, first we process it and get all entities and their tags. And then we start by the augmentation module. If the word is an entity, we have the sentences, and if the word is an entity, we go to the fast text analogies method that replace an entity with most probably a similar entity or another word with the same type. And then if it's not an entity, and we are in the second or the first variation of the model to replace all the words in the sentence, we get the nearest neighbor word, and we try the different variation, whether the first nearest or the second or the third, and so on. And then the second variation of the word embedding substitution is the classical one, the contextual one. We used the well-known BERT embedding model, and we used another model, which is Kermit, and Kermit is a contextual embeddings that is trained on Arabic English code switched embeddings. We started by masking an entity to augment, and then we select the top 10 words that have the highest probability to be similar to the masked word, and then we select from the top 10 the one with the same, we tag all the 10 words, and then we select the same word with the same tag, the word with the same tag. Then moving to the second technique, which is the modified ADA. The initial ADA technique consists of synonym replacement, random insertion, and random swap, and random deletion. Here we have some parameters that we need to define. The percentage of words need to be augmented, the number of sentences that we need to generate. Here, this is the general architecture. We modified 2 main operations that we thought that will be useful, which is the synonym replacement and the random insertion. The main model didn't support Arabic language at all, so we created the WordNet for Arabic and the wiki synonym extraction as well. We added it to the ADA technique. We used the back translation. We created 3 variations from the back translation using Tensor to Tensor library, using Google Translate, and using Google Translate, and we tried to have 2 intermediate languages instead of 1. This is the general architecture of the back translation. We count the number of English words, we translate to Arabic, we translate to the intermediate language, and we translate back to Arabic. And in order to preserve the code switching behavior, we choose n random words to be translated to English. We applied an extrinsic evaluation method, which is selecting a specific NLP task and applying data augmentation techniques on the original data, and training the model or the technique, the approach, the task with and without this data. And in our case, we selected the MER model that was previously implemented and achieved 77.69 F-score without our data augmentation technique. And we started running or evaluating the model after applying or augmenting the training data. So this is the results of the first technique, which is the synonym replacement, and actually it didn't improve. However, we tried also to the two operations, synonym replacement and random insertion, and it actually improved to 78.43. And here, this is a summary of all the variations of we have first, in the first set, the ones of the word embedding substitution. In the second set, the back translation. And as we can see, we tried to combine the back translation with the first technique, which is the word embedding. And actually, this achieved the highest model here in red, which is the back translation, along with substituting the entities. So we can have a more different or variant sentences containing entities, and we achieved 97.2. And this is statistics about the data before, the number of entities before, and the number of entities after applying the technique. So we can see that the original data set contained around 14,000 entities, and after the increase, we will have more than 21 entities. This is using the first augmentation technique, or the highest, and this is using the second highest augmentation technique. And also we applied, in order to make sure of the quality of the generated data, we tried to get a sample of random 100 sentences, and we manually checked their semantic, whether they are correct or not. And we found out that 70% of the sentences are meaningful and understandable. As a conclusion, we are tackling a general problem of the lack of data, and we selected the name entity recognition to try to generate artificial data for such a task. We, as a future work, we want to enhance the existing DA techniques, and we want to apply a validation technique to check the assigned labels, the tags, and we want to implement an automatic technique to check the quality of the generated data. Thank you. Any questions?
Okay, thank you very much. I'd like to open the floor for questions. If anyone would like to ask Caroline any question. Okay, I'll ask. We still have time, so I was hoping someone else would. But first of all, let me just say that I'm impressed by the quality of this work. Very impressive work. My question is quite simple. You've used a lot of translation, so how did that impact the performance of the system? I mean, did you do any error propagation analysis to see the effect of translation? Of course, the whole idea is data augmentation is to generate everything automatically, but I was just wondering if the translation step didn't generate a lot of noise.
No, it's actually, it wasn't easy. That's why when we started our approach with the library tensor to tensor, we checked the quality of the translation, and the blue score was very low, and we didn't achieve a good translation. So that's why we moved to the Google Translate to have better quality of the translation. So it was a little bit, we didn't investigate error propagation more. However, what we checked quickly, that for sure we faced a problem in the translation, and enhancing such a technique is one of the proposed future work.
Thank you very much, Caroline. No other questions? No one wants to ask anything? Okay, in that case, our next presentation is in about 6 minutes. Again, we'll have to wait because we're synchronizing with the other session, and we'll start in exactly 6 minutes. now.
Hi, this is Ahmed Sahlul from Taki Health. I'm going to present my paper named Medflair Name Entity Recognition for Diseases and Medications based on Flair Embedding. Our motivation is that as we know that electronic health documents contains many informations. Some of them are personal information from patients, others are medical informations. So like such as diagnosis, medications, treatments, bills, and other stuff. So these information need to be digitized to be processed appropriately. So as we know that narrative text is more complex and needs more powerful tools for to be pre-processed and to be digitized. So such type of problems need like it's a bit a challenging problem. So there are a position in the medical system called medical coders, who are people that are uh, like uh, who are like in charge of extracting the medical expressions from the whole medical forms, which can be like for 20 or 30 pages for each medical record. So their works is to or their tasks is to extract like medical information, which can be like uh, medications, diseases, and procedures as well. This is important because sometimes some things happen like which cause errors such as difficult coding process or overbilling or underbilling because you extract the wrong numbers, which consequently can lead to legal issues. Also, it can waste of money and income for hospital and as well as the budget. So we have built a model, a deep learning model based on name entity recognition that work on extracting diseases, medications, and medical lab tests from the whole medical report and extract these entities. So this is the main architecture. We have here the electronic medical health or electronic health document record as input, and we have an output like indications, diseases, and lab tests. And inside is the engine of our model, which mainly the brain of it is the deep neural networks. And we have here like a pre-trained model on a very huge dataset contains of 25 millions of abstracts from biomedical articles. Some of them are from PubMed, others from BMC, and others from other corpora. So it is a very huge or a little bit huge model. In terms of the architecture itself, as seen here, that it contains of in the beginning, the model was trained on a bidirectional long short-term memory, which is and then a by LSTM layer, which contains of like a forward and a backward layers. The first one contains of 265 nodes, and the second one is like that, the same. So we have a little bit huge model, and then the last layer is a CRF, conditional random field layer for sequencing tagging, because we it's a context aware model, so we have to be aware of each word and each the second word and the previous word of it. So it's a context aware model, so it has to be aware of the medical entity and its position in the world. Our model has been trained on different data sets. Some of them are based on diseases, such as these data sets. Others were trained on drugs or medication data sets, such as this and this. So we have varieties of number of annotations, starting from like 6,000 till about 80,000. And then we have trained these models, or they're actually trained the training sets of it on some titles, and then validating, then testing. So we have a pre-trained model that has been trained perfectly. So in order to measure the performance, we have here test our model on these data sets. So we get a good number of accuracy as well as F1 score. We have here like in these data sets 99 accuracy, and here 95, and the least one is 88 for F1 score for these data sets, because it's a medication data sets which can be varied in some medical expressions. Also, we have make a comparison between our model Midflare and the other pre-trained models or very popular models such as BERT model, Near model, Pioneer model, and the Pioneer Flare models. These models are very specified and very popular in the area of NLP and the name entity recognition. Exactly, some of them has been just published in 2020, such as this, and this. So this is a performance measure. Our model here, Midfield, it can see that it compete all the other models here in F1 score in most of the data sets here, except of the data sets which contains medications, but it's a slight different, like 1% for F1 score. The same here, Midfield has compete all other data sets on all data sets except this data sets which contains medications. The same here with the pink one, which represents the Midfield model. So this is our discussion that we have built a pre-trained model, which means we save time, we save computation time. It's pre-trained, so we just transfer learning, we just initialize it, so it has been trained. We tune it based on our new data set, so we perform the resources consumptions uh, as well as we keep the model deep. The second thing is that these models has shown a great generalization and fast convergence, because they are very specified in a very specified tasks which uh, belongs to medical expressions or medical texts. The third thing is that they are adapting on contextualized and word embedding. So because they were trained previously on like 25 millions of abstracts, so they're trained perfectly on a very specific domain. It shows also advantages among other deep models, such as BERT, which is a very popular model and shows advantage in other medical or other uh, general NLP tasks. The last thing is that we there is no need to manual feature engineering or pre-processing on features or performing like noise removal or correlations or such as feature selection on features. We take the model as it and we work on it as it. So our AI could achieve both automation, because this is versus the human coders, which like you can hire a lot of people and spend much time in doing the same process, but you automate it perfectly, as we see in the results. We perform it in highest performance. We compare this performance among other like coders or human coders, and it shows advantage. We achieve also lowest processing time because each medical record is accessed or digitized in part of seconds, so it takes no time. So, as it was a challenging task to process a little bit huge medical records which contains varieties of informations like billing information, personal information, age, mail, and other stuff, and other stuff. But also we do it sufficiently using deep neural networks, and we train our neural network to extract only medical expressions, which are diseases, medications, and lab tests in a short time. So, thanks for listening.
Okay, one more time, we find ourselves with a presentation without the author to answer any questions. So I'm just going to ask anyone who has any questions to please email the author directly. In about 8 minutes, we're going to start the next presentation, which is actually going to be delivered by myself. And the title of this presentation is QDetect, an intelligent tool for detecting Quranic verses in any text. I apologize that we have to wait, but again, in order to synchronize with the other session, we're just going to have to wait for 8 minutes, and we're going to start at 2:40 on the dot GMT time.